Welcome to our presentation of our Design for Manufacturability report for a hand grind coffee grinder. We are Group 4 and we're made up of Austin, Benjamin, Ethan, Jason, and Jay. Our product is a hand grind coffee grinder designed to keep a consistent grind size, hold the coffee beans, catch the grounds, and we're estimating to make about 100,000 of these per year. This is the initial model of our hand grind coffee grinder. Here's the exploded view of that model. You can see the main shaft assemblies located on the middle of this exploded view, with the exterior components on the left and the rest of the components on the right. Our primary customers are those who enjoy fresh ground coffee on the go. We expect them to make up 75% of our market. Our secondary customers are coffee enthusiasts looking for cheaper options compared to expensive electric coffee grinders, and we expect them to make up about 25% of our market. The main functions of the coffee grinder are it needs to contain beans, crush beans, adjust the grind size, guard the hands, seal grounds, aid grip, observe the grounds, and provide a smooth body. Here we have the functional component mapping matrix where we can see each of the components of our coffee grinder and how they address the functions that I just went over. Here we can see on the left all of the things that both customer groups will see, and the secondary customers don't need as enhanced of a grip and they don't need to be able to see the grounds. Here's our quad chart. We can see that many of the components can be completely eliminated, as well as many of them we look to redesign. Here's our component commonality table. On the left, we can see all of the parts that are shared between the two models, and on the right, we can see that the lower trap and the handle knob are the two components that we change to differentiate. Here is the knob. We can see that the secondary variant is larger and it provides a better grip. And here's the lower trap. We can see that the primary variant is opaque and the secondary variant is clear. Here's our assembly diagram. So in the modified assembly sequence, we move down as far as we can until we get to the handle knob where we have the two different knobs, and then we move along where we also have the two different barrels.
So here you can see this is our design for manual assembly of our original design. We decided to pick our platform part to be the drive shaft and our module part to be the lower trap. And then from doing these calculations, we got a total time to be about 132 and efficiency to about 47. From here, you can see that we made design changes to our drive shaft, and what we did by doing this is we reduced the number of parts. Using the shaft, we replaced the handle plug plastic and handle spud, which also eliminated the need for lid lock top plastics, and this simplified overall assembly and other parts by removing top threading from the shaft and removing the handle spud lock, which can be seen in the after image. You can see here, this is the lower trap that we decided to do. And from here, we made it a little bit taller, and we did this by combining the CG barrel lower and the lower trap to reduce the number of parts. And we combined the lower trap and lower trap retainer to also reduce the number of parts. From here, you can see this is the design for our manual assembly of the redesigned. And again, you can see that there's 13 parts versus 23 from before, and we were able to increase our efficiency to 56.87 and decrease our total time to about 63 seconds. And here you can see this is our design for the automated subassembly. These are indicating all the various parts that are listed on the left-hand side. You can see that this is our calculations for the automated assembly of these 7 parts, which we got to be about 15.58 seconds. We wanted to redesign the CAD to obviously simplify and remove any unnecessary components by redesigning both the drive shaft and the upper housing. And we saw that by doing this, the assembly came a little more complicated, but it also removed the need for the upper and lower subassemblies that we previously had in our original design. Here, this is the calculations for the design for the automated subassembly. And you can see that we reduced our total time to 2.4 seconds. We're able to include more parts in our subassembly to decrease the overall assembly time.
These are the two redesigned components we selected to do our process selection and further analysis on. The first is the drive shaft, which was modified in the manual assembly, and the lower trap, which was also modified in the manual assembly. On the slide, you can see that there are some cross-sectional drawings of the updated components with some key features noted. For the drive shaft, the overall length is now 110.57 millimeters, and you can also see that there's the M6 threads on the left side of the drive shaft. For the lower trap, we can see that the overall height is now 100.9 millimeters, as well as the locking mechanism in the top right has a dimension of 3.5 millimeters. From those key features I just mentioned, we determined those that are critical to our product's function in order to base our tolerances on them. For the drive shaft, nearly all the dimensions are deemed critical for performing the functions, which are crushing beans and adjusting grind size. However, we decided to focus on the M6 threads since that interface is more defined, and from screw tolerance tables, we decided to use a tolerance of plus and minus 0.05 millimeters. And for the lower trap, the locking mechanism on the top is the most critical dimension in performing the function of sealing grounds. Since that feature connects the lower trap to the rest of the body of the grinder, the rest of the body also performs the function of sealing grounds. A tolerance of plus or minus 0.1 mm was used for this dimension, using a ISO standard for small linear dimensions. From the different manufacturing methods, we filter them down using these capability attributes listed here, starting with material and shape of the parts, then using the parts masses, section thicknesses, tolerances, surface finish, and finally economic batch size to select one process per part. So starting with material, for the drive shaft we chose a ferrous metal, steel, and for the lower trap we chose thermoplastics. And then next for shape, both the drive shaft and lower trap were 3D solids. For the mass, the drive shaft we calculate to be around 20 grams, and for the lower trap to be around 35 grams. For section thickness, from these drawings that I showed before, the drive shaft minimum thickness was 4 millimeters, and the lower trap was 1.27 millimeters. For tolerances, like I mentioned, we used 0.05 millimeters for the drive shaft, and then 0.1 millimeters for the lower trap. And for surface roughness, we're not very concerned about it, so we had each part as 10 microns. And then finally for economic batch size, since each part only appears once per coffee grinder, and we're aiming to produce 100,000 units each cycle, each part has 10 to the 5th units. And then for our final manufacturing recommendations, we recommend machining the drive shaft from steel, and then injection molding the lower trap from thermoplastics.
On the left is the drive shaft post-DFA and before redesign for machining. On the right is the drive shaft after redesign for machining. We performed analysis using DfM Pro on the post-DFA drive shaft to obtain redesign ideas. From left to right, we gave a radius to sharp internal corners. We also replaced radiused corners with chamfers. Finally, we removed deeply radiused features. For the drive shaft before redesign, we extrapolated the unit price data provided by hubs to obtain the unit price at our batch size of 100,000 units. We assumed the manufacturing cost as 80% of the quote to get a part cost of 8 cents. We performed the same process for the drive shaft after redesign to get a part cost of 5 cents. This is how our analytical cost estimations compare with our price codes from hubs. The before design and after design were estimated to have the same cost when analytical methods were used. This is because due to limitations in our analytical methods, the cost benefits of the redesigned features, such as the removal of radius corners, were not captured. Also, the price codes from hubs were found to be significantly lower than their counterparts. This is due to bulk discounting and the long range of extrapolation done for the hub's quote.
For the lower trap, which is our injection molded part, we have two different versions. We have a polycarbonate version that's transparent and a 6/6 nylon version that's opaque. This is the design for injection molding cost analysis for this part based on these two different materials. As you can see, the machine cycle time is fairly high. This is due to the maximum thickness of the part and the cooling time. So we're looking at a total cost per part of 57 cents for the polycarbonate version and 50 cents for the nylon version. After running this part through DfM Pro, it highlighted 3 issues for us. You can see there's an undercut that's used as our locking mechanism. There's no draft angle on the internal faces, and the wall thickness is not very uniform across the part, specifically at those high points on the triangles. To remedy these issues, we made 3 design changes. We reduced the thickness and overall size of the locking feature to minimize the undercut. Unfortunately, we can't eliminate this entirely as it is the locking mechanism. The maximum wall thickness was also reduced at these high points on the triangles to make the wall thickness more uniform across the part, and a draft angle and some internal radii were added to the internal faces to aid in releasing the part from the mold. So after these changes, we see the machine cycle time decreased greatly, reducing the total cost per part to 48 cents for the polycarbonate version and 39 cents for the nylon version. A service that we offer with this product is a warranty service, which runs within 1 year of purchase of the product. We have representatives that troubleshoot issues with the product and will send you free replacement parts. This minimizes costs to the customer because they don't have to buy an entirely new coffee grinder. They're able to just replace 1 or 2 parts. This also benefits the environment because it prevents the need to throw away the entire product, and we are reducing waste by instead replacing individual parts. So in conclusion, the benefits of our design changes is that we reduced assembly time by a factor of about 1/6 through DFA and reduced manufacturing costs by just over 20% through DfM. The pros of our design is that we reduce assembly time and manufacturing costs as well as part count. And then the con of our design is we actually increase the overall size of a machine part, increasing material costs for that particular part, even though we decreased manufacturing costs overall. If we were to start over, we would choose an alternate subassembly to analyze for automated assembly, perhaps the handle or outer body rather than the drive shaft. Thank you for listening to our presentation.